Hello everyone and welcome to the Mathematiker channel. Let's suppose that we have a prime number that we note, p. We would like to prove, in two different methods, that whatever the natural number a, if p divide the square of a, then p divides a. So, let's start with the first method, which relies on the proof by contradiction. We have, p divides the square of a. In order to prove that p divides a, we're going, at first, to suppose that p doesn't divide a, and develop this hypothesis to a contradictory result. We can then conclude that p divides a. So, if p doesn't divide a, and since p is a prime number, then p and a would be co-prime. This means, according to Bezout theorem, that there are two integers that we'll note, u and v, such that p multiplied by u plus a multiplied by v equals 1. By multiplying this equality by a, we'll find that p multiplied by u multiplied by a plus a multiplied by v multiplied by a equals a. If we note u multiplied by a as u prime, we would find that p multiplied by u prime plus a square multiplied by v equals a. But p divides the square of a. So, p divides a square multiplied by v. Therefore, our equality become p multiplied by u prime plus p multiplied by v prime equals a, assuming that p multiplied by v prime equals a square multiplied by v. This means that p multiplied by u prime plus v prime equals a. So, if we note the sum u prime plus v prime is w, we find that p multiplied by w equals a, such that w is an integer number. So, p divides a. And this is a contradiction with our assumption that affirms that p doesn't divide a. We therefore deduce that p divides a. And this proves our implication according to this method. Let's now check out another method. This second method relies on a proof by contraposition. This means that, in order to prove the implication, p divide the square of a, implies that p divide a. We're going to prove that, if p doesn't divide a, then p doesn't divide the square of a. So, if p doesn't divide a, and as p is a prime number, we would have p and a as co-prime numbers. This means that there are two integers, u and v, such that p multiplied by u plus a multiplied by v equals 1. By raising up both sides of this equality to the power of 2, we find that p multiplied by u plus a multiplied by v all square equals 1 square. This means that p multiplied by u all square plus 2 multiplied by p multiplied by u multiplied by a multiplied by v plus a multiplied by v all square equals 1. Which implies that p square multiplied by u square plus p multiplied by 2 multiplied by u multiplied by a multiplied by v plus a square multiplied by v square equals 1. Now, by extracting p as a common factor from the first two terms of the left side of this equality, we find that p multiplied by u square plus 2 multiplied by u multiplied by a multiplied by v plus a square multiplied by v square equals 1. This means that p multiplied by u prime plus a square multiplied by v prime equals 1, assuming that u prime and v prime are integer numbers which equals respectively p multiplied by u square plus 2 multiplied by u multiplied by a multiplied by v and v square. Therefore, p and a square are co-prime. So, p doesn't divide the square of a. And this proves our contraposition, which mean that our initial implication is true. So, these were two different methods to prove that, for a prime number p, in order to divide the square of a natural number a, p must divides a. Can you now prove that for a prime number p, in order to divide an n power of a natural number a, p must divide a? Let us know about this in the comment section. Thanks for watching the video, and if it was enjoyable, please hit the like button and subscribe to the channel for future publications.